Hello. So my
To continue now, we have to Professor Felipe Chavez introduce to Professor Takeo Takahashi. You can start, Felipe.
Okay, welcome everybody to the continuation of our seminar. And after the very nice talk by Professor Pierre, we are having the pleasure to have the opportunity to see a talk by Professor Takeo Takahashi. Professor Takeo is director de recherche in here, Nancy, in France, in the Institut Elie Cartan. Okay, and Professor Takahashi is a very well-known mathematician working on control and fluid structure problems with very nice results. I believe many of you have heard or read some of his ideas and papers. So it's really a pleasure, Takeo, and okay, the palco is yours.
Okay, thank you. Obrigado. So yes, thank you for this presentation. So I'm glad to do this talk today. I'm very happy about this invitation. This is one of my first talk the beginning of the COVID, so I'm not used so much about this tool with Zoom and so on. So I hope I will do everything correctly. So the work I will present today is a work in collaboration with Mehdi Badra at the University of Toulouse, and deal with the interaction between a fluid and a structure, and more precisely, the fluid will be incompressible and viscous, and the structure will be located at the boundary. So if we go to a picture, you have this domain F and this theta where you have the fluid, and you have a boundary around a gamma -1, which is the bottom boundary, which is fixed, which is not moving, and an upper boundary gamma eta, which is moving, and the displacement follow a structure equation like the beam equation or the wave equation. So we will use inside the fluid domain the standard Navier-Stokes equation, and we will use different structure equation for the equation of eta. So to simplify also, I will assume that there is a periodic condition in x1. So instead of using the interval 0L, I will use the torus calligraphic E, so that I don't have to take care about anymore the lateral boundary condition. So to present the system, I will first present the fluid equation, which is quite well known. This is a Navier-Stokes system. You have the time derivative of u plus the nonlinear term u gradient u. Both of them are the material derivative, which is equal to the divergence of the Cauchy stress tensor. So usually you develop this Cauchy stress tensor and write it as minus Laplacian u plus gradient p. And you have then this first equation for u, and you have also the incompressibility condition divergence of u is equal to 0. So I choose to keep the divergence of the Cauchy stress tensor because I will use it after that for the structure equation, the Cauchy stress tensor, and this is just 2 times the symmetry gradient of u minus p identity.
Takeo,
for the structure equation, so
Takeo,
first I have to explain this definition gamma eta. So this is the curves corresponding to x1 1 plus eta. So if I go back to my drawing, this means this is this domain. Yes, see?
Sorry, I believe the slides are not going. You are not passing the slides.
In the first one.
Yeah, you are still in the first one.
Okay, let me. Okay. It's better like this.
Yeah. Now it's good. It's passing.
Okay. See if I put in plan in. Okay. So yes. Okay. So I go back to the drawing. So the drawing was here. You have the at the bottom gamma -1, at the top this gamma eta. The fluid domain is denoted by f eta, And as I explained, so the bottom gamma minus 1 is fixed, and the gamma eta is moving according to the wave or the beam equation. And you have this lateral boundary condition, which where you assume that there is a periodicity. So the Navier-Stokes system is this system. You see now the change of slide, or is it okay?
Yes, Takeo, it's working.
Okay. So the Navier-Stokes system is this one. So you have time derivative of u plus u gradient u, which is the material derivative, divergence of the Cauchy stress tensor, which is written here. And when you develop it, you have minus Laplacian u plus gradient p. And the incompressibility condition, divergence of u. So as I explained, I will use after that the Cauchy stress tensor, which is 2 times the gradient of u minus p identity. And it's E2 because I am in dimension 2. I'm sorry, but small mistake. So the structure is gamma eta, which is x1, 1 plus eta. And that's why in my drawing here, gamma minus 1 corresponds to the curves corresponding to x2 is equal to 0. And if there is no deformation in the upper boundaries, this will be x2 is equal to 1. That's why I choose to put this 1 plus eta here. So let's say the referential case, eta equals 0 is just for x2 is equal to 1. And for the structure, I will consider a very complicated system because I want to have many possibilities. You can after that consider that alpha, beta, and gamma are equal to 1, but this is more or less a plate equation which corresponds to the alpha and beta, let's say, and the damping is due to the gamma second derivative in x1 and first derivative in t of eta. So if you multiply, you forget about the h eta and multiply by dt eta this equation, then you will see that the last term corresponds to a damping. And we will neglect all the exterior forces. So the only force which apply to this plate equation is a force which can be expressed through the Cauchy stress tensor T of UP. And you have also the appearance of the geometry here, which is here. So the boundary condition for the fluid, since you have periodic boundary condition at the lateral part of the domain, you will just have a boundary condition at the bottom, at the top of the domain. So at the bottom, I will and at the top, I will assume a no-slip boundary condition. So at the bottom, it's simple because nothing is moving, so it will be just u is equal to 0. And at the top, I will have to follow the velocity of the displacement. And this displacement is just in the direction E2. So this will be the time derivative of eta times E2. So now if I put all the equations together, you have this Navier-Stokes equation written in the moving domain f of t, then the boundary condition, the no-slip boundary condition, the damp beam equation with the right-hand side corresponding to the force of the fluid acting on this beam equation, and I want to analyze this coupled system and show the well-posedness of this system. And in order to do this, before even trying to study the well-posedness, usually what we would like to do to see at least if it's correctly written is to do some energy inequality. So I begin with this. To get an energy inequality of this system, first I will multiply the Navier-Stokes equation by u. This is a standard way. And for the damp beam equation, for it's usually a beam equation, I multiply by dt eta to have the energy inequality. So for the fluid, I multiply by u the Navier-Stokes equation, and I separate the material derivative and what corresponding to the Cauchy stress tensor. So for the first part, you have dtu times u. So this corresponds more or less to the time derivative of u squared divided by 2. And what you would like is to pass the time derivative outside the integral. And what is the problem is that the domain is moving, but this is well done. In fact, the u gradient u is helping. So this is a Reynolds number, which says that the material derivative is exactly well done, so that this expression is the time derivative of the integral of f of t of u squared divided by 2. For the other part, the Cauchy stress tensor, we do integration by part in space, and after some standard calculation, you have 2 times the symmetric gradient of U and the boundary term, which is of course equal to 0 if you have a fluid without any structure. Then you are done, and you don't have this boundary term which is remaining. So you have to deal with these boundary terms, but you have, of course, the structure also to deal with. You multiply the damped beam equation by dt eta, and the integration by part here is very easy because you have no boundary. E is a torus, so you can do the integration by part very easily, and you recover what you usually get for the wave or for the beam equation, the time derivative of dt eta square, and some part which is the second derivative of eta in space, or the first derivative of eta, depending if you are working on the beam or of the wave equation. You have, as promised, the damping corresponding to the last term, and you have, of course, to deal with the force acting, the force of the fluid acting on the beam, which gives you a term written in the torus. So now, without this force, everything will be done, but you have this term remaining. You have also the boundary term from the fluid, and you have to compare them to see if everything is well done. So you rewrite the boundary term coming from the fluid in the part where it is not equal to 0. So you have a change of variable to do, which gives you the square root of 1 plus the square of dx1 eta. And utx1 eta tx1, because of the slip boundary condition, another slip boundary condition, it is equal to dt eta e2. And when you put everything together, you recover exactly the right-hand side associated to the beam times dt eta. And this means that the both terms which were remaining in the energy inequality disappear together. And you get something very simple, which is this energy equality or inequality, which will show that everything is well done. And you could look for a weak solution with this energy equality. So for the fluid, you will look for something very standard, which is L infinity L2, L2H1. And for eta, because of the second time derivative, it's a bit more complicated, but you will get something also which is quite standard for weak solution. Here, my talk will not be about weak solution. It will be about strong solution, but I wanted to show this energy inequality before starting. So instead of looking weak solution, I will search for solutions which are more regular. And the aim, more or less, is to look for solutions such that all the terms in the beam equation or in the Navier-Stokes equation are L2 in time and space. So it means that more or less I want to look for a velocity which is h1 in time, in L2 in space, L2 in time, and h2 in space, because of the time derivative of u and the Laplacian of u, and p which would be L2 h1. And for eta, because of the fact that you have more derivatives, you will look for eta h2 L2, L2 h4, and because of the damping, h1 h2. In fact, you can get something more because the h eta of up is like the trace of u and of a gradient of u and p. So this means that the h is in fact in L2 h1 half. So this means that eta, you should get something more than what is written here. You should get 1/2 more in space. So some other remark about the system, which can be done by simple calculation. First, if you integrate the incompressibility condition, divergence of u is equal to 0 on the fluid domain. By integration by part, you recover that this is the integral on gamma eta of t of u dot n. And because of the no-slip boundary condition, you can obtain that this is a time derivative of the integral of e of eta. So this means that if at the initial time this mean of eta is equal to 0, it will remain equal to 0 during all the times. And this is something which is physically normal, because you are working with incompressible fluids, which means a conservation of volume. So it means that the displacement should satisfy some kind of condition like this to preserve the volume of the fluid, of the domain of the fluid. But because of this condition, if you use this mean of eta equal to 0 on the beam equation and integrate so all the beam equation in E, you find that everything is equal to 0 except the Cauchy stress tensor. And if you rewrite it in a more precise way, you see that you have the mean of P on this E, which is equal to something corresponding to the gradient of U. And this means that with this is a difference with the usual standard Stokes or Navier-Stokes equation, where the pressure is given up to a constant. Here, it's not given up to a constant. The constant is determined by this last relation, which is complicated, but which defines the constant of the pressure. So since we are working, we like this, in fact, for the fluid, this possibility to have a constant pressure which is given up to a constant. I will change a bit the system I'm working with by projecting the beam equation into the space of mean equal to 0 and in the orthogonal. So the last equation, the equation for the beam, I will project it with PM, which is the projection on the space with mean equal to 0. And I will also add, this means that for the first part, the first part of the slide, the pressure is given up to a constant. And then at the end, when I solve all the system, I will determine the constant of the pressure by the last relation, which is the relation I written in the previous slide. So I will work from now on the equation of the Navier-Stokes equation and the mean equation projected on this space with mean value equal to 0. So now some few slides which are quite ugly, and please don't read them because they are quite awful. We just say that lots of people have worked on this system. They have worked on weak solution, strong solution, and many other things. So the reason that there is so many works on this system is it is easier to treat than a standard Navier-Stokes equation coupled with an elastic structure, but an elastic structure located let's say in the interior domain. So if you have a domain for the fluid and domain for the structure and you couple them, usually you have the same dimension for the fluid and for the structure, and this is much more complicated to study. Here, because of the structure located at the boundary and written on the boundary of the fluid domain, you have a dimension less important for the structure than for the fluid, and it allows us to do more analysis, and this is why there are so many works on this. So one part of the work is dedicated to the fact that you want to remove the damping in the beam equation, and there are also some work on boundary stabilization and on control. So I will detail a little bit how we manage to solve this system, and the first step is quite standard. So you don't work on a moving domain, so you have to change you have to use a change variable to reduce the fluid domain and to have a fixed fluid domain. And here, because the tree is very simple, you can do something which is quite easy. You can just do a dilatation in the x2 direction to reduce the domain to a fixed domain. So you can do the case where you reduce the domain to the rectangle. So this means eta equal to 0. That is the first transformation x of t, which is with f0 of gamma 0. This is a rectangle with x2 is equal to 0 and x2 is equal to 1. But in some cases, this is not the good change variable. It's not the good domain of reference. You can also do a change variable to reduce everything in the domain associated to the initial displacement, which is better, for example, when you do a local in time existence. So there are also many other change variables which are possible and much more complicated. It depends a lot of what you are doing. But once you have a change variable, you of course you can recall for simplicity f and gamma without any indices the domain which is now fixed, which corresponds, for example, to the initial configuration, and you will change u and p by v and p by composing by this change variable x. And sometimes you can do, of course, something more complicated by multiplying by some matrix before u for example, to keep the divergence, the divergence-free condition. So if you multiply by a good matrix corresponding to the change of variable, if divergence of U is equal to 0, then divergence V remains equal to 0, which is something better for the study. After many calculation, many computation, which is very unpleasant, you obtain lots of coefficients for the Fried equation. And if you put everything in the right-hand side, so this is what I'm doing, you don't see so much. And you put also the nonlinear term V gradient V on this F of V pi eta. Also for the beam equation, the force acting from the fluid on the beam, there is also some transformation. So you put all the transformation in this H of V pi eta, the last term on the beam equation. And you find that you have a very nice system, a Stokes system coupled with a damped beam equation. But of course, you have to deal with all this nonlinear term coming from the change of variable. And the idea is to first study the linear system when you replace this nonlinear term F of V pi eta and H of V pi eta by a given right-hand side, and then try to do a fixed point argument. So this will basically what I'm going to present in this talk. I will consider the coupling, the linear coupling between a Stokes equation with a given right-hand side F and a damped beam equation with a right-hand side given, which is small h. So they are given, the domain is now fixed, and you just want to couple, in some sense, the Stokes equation with this damped beam equation. And the idea is to understand if we can already, for this linear system, obtain a well-posed result. And this is to do this, I will introduce some operator as Pierre did in his talk. I will try to show that the corresponding operator generate an analytic semi-group. So I will introduce an operator, two operators, in fact, for the structure equation. So A1 for the main operator, A2 for the damping. And what you see is the domain of the A1 is H4, the domain of the damping is H2, so that you have that the domain of the damping is the domain of A1 1/2, and this will be very important for the future. So the structure equation can be written in a, let's say, a more simplified way, where you have dt, the second derivative of eta plus A2, the first derivative of eta plus A1 eta is equal to the force of the fluid on the structure plus a given H. You also want to rewrite a little bit the boundary condition, because you always have two boundaries, so it's a bit unpleasant. You have something on gamma -1, the bottom boundary, and on the up boundary gamma. Lambda to write both condition, and this operator lambda is also very useful because you can write the force of the fluid acting on the structure in a better way by using the adjoint of this operator lambda. So this force can be written by lambda star times the Cauchy stress tensor TVPN. So using this lambda, you can rewrite all the previous system as here. So you have the Stokes equation with the right-hand side F. The boundary equation are written in a condensed way by this operator lambda. And you have the damped beam equation with the lambda star TVPN plus the H, which is given. And all this system, you want to write it in a abstract way. Y prime is equal to AY plus a given large capital F. So you have to write the operator A by here by using introducing some set. So the first set is the set H, which is W, eta1 and eta2. So you have two eta because of the fact that you have a second derivative in time. So you have to write it in order 1 by introducing eta1 and its derivative eta2. And you have a space which is very similar to what you have for the Stokes equation, with a divergence equal to 0 and the condition, the normal component, which relies W and eta2. And you can introduce the orthogonal projection PH from L2 times D1 half times HS. So I recall that the domain of A1 half is more or less H2. So L2 times H2 times L2 onto the space H, where you have the divergence and the normal component. And then you can introduce the domain of A, and you have as standards W, which is H2, eta 1, which is H4, eta 2, which is H2, with the divergence condition and the no-slip boundary condition, which is condensed by the operator lambda. The operator A is the projection of H of Laplacian of W, eta 2, and what the beam equation here. And by some standard functional analysis, you can show that A generates a C0 semigroup. But of course, this is not sufficient for us. You want to show more to get the good result. So here I show that I say that if I introduce the unknowns W, eta 1, eta 2, and I write it as y, then I have that y prime is equal to ay plus f, and I want to show some good property on A to have that the linear system is well posed, and that I can do after that a fixed point argument. So the good framework is the case where A is generating an analytic semigroup. So this means that the mapping from T to exponential TA is analytic, but this is not what I'm going to use. I'm going to use the maximal regularity, which says that the equation y prime is equal to ay plus f with initial condition y0. If f is in L2 with value in H, y prime and a1 are also L2 with value in L2 with value in H, and the initial condition should be between let's say the domain of A and H. So this introduces A power 1/2 here. So usually, if you have in this framework, you can do after that a good fixed point argument. So the idea is to show that in what I presented before, you are in this case that the operator A is generating an analytic semigroup. And to do this, by introducing a sector lambda sigma beta, which is located with a vertex at 0 and with an angle beta which should be greater than p over 2. And you have to show that such a sector is included in the resolvent of A, and that in this sector, lambda times lambda identity minus A power minus 1 is bounded uniformly. So this is these two conditions which allows you to show that the operator generates an analytic semigroup, so that you have the maximal regularity and everything will work perfectly after that. So to show this resolvent estimate, I rewrite what means lambda minus A V eta 1 eta 2 is equal to FGH. So this is this coupled system. You recognize as two equations which condition with between V and eta 2, and you have then this Undamped beam equation written in the first order equation here, and you want to show that lambda times the solution of the system V eta 1 eta 2 is less than a constant times the right hand side FGH in the norm H. And this is quite complicated to show in some small slides. So I simplify a lot, and I will take f and g is equal to 0. So here you have 0, here g is equal to 0. So the only equation which is remaining in some sense is the beam equation. So I will introduce the solution of this Stokes system lambda v minus divergence of t is equal to 0, divergence equals 0, and the condition v is equal to lambda eta 1, which correspond to the first part of my system when f is equal to 0. And I will need the lambda star associated TVPN associated to the Stokes system I will call it L lambda. So if you think about, for example, let's say the heat equation, instead of the Stokes equation, this operator lambda, L lambda is just directly to Neumann operator, so which corresponds to the force of the fluid acting on the structure. And it remains for the structure equation, the resolvent equation associated to the structure is here given here. So you recognize in some sense the beam equation. All the time derivative correspond to a lambda. So you have lambda square eta 1 plus lambda eta 2 eta 1, which is damping. The lambda L lambda eta 1, which is what is coming from the fluid, plus A1 eta 1 is equal to H. And you want to show that on this damp beam equation, where there is a fluid acting on this beam equation, you want to show the resolvent equation, which is written here with eta 1 and AY eta 1. So it's much easier to see this. And what I'm going to use is an old result of Chen and Trigiani, which says that if you have a damping A2 and this damping is behaving like A1 power 1/2, then you generate an analytic semigroup, which says that the resolvent equation is satisfied the one I want, except that in this resolvent equation, I don't have the part coming from the fluid. So if I rewrite the resolvent equation I want to solve here with L lambda and rewrite the Chen-Trigiani estimate for the resolvent, the only thing which is remaining to do is to see what happened with the L lambda coming from the fluid. And here it's easy to do because it's a lower order term. So you just get rid of this part, and we get that the operator associated to the beam with the action of the fluid is still generating an analytic semigroup. So this will allow me to show that the coupling between the damp beam equation and the Navier-Stokes equation is well posed. I can show, for example, the local in-time existence by this. But this is not so exciting because, in some sense, the damping I put in the beam equation, the term corresponding to gamma, change the structure of the beam equation so that the structure now is the beam equation is a parabolic equation. The Stokes equation, the linearization of the Navier-Stokes equation is also parabolic. So I'm just coupling two parabolic systems, but at least it is working. The difficulty here was at first to understand how to do this and to deal with the change of variables that I'm hiding here. We can also extend this kind of thing to the LP-LQ framework, which is something I did with Deba and Maiti, which is a researcher in Bangalore in India. So the real work starts when you want to remove the damping and when you want to study the undamped plate equation or the undamped wave equation coupled with a fluid equation. Here you have really a coupling between a parabolic equation, the Navier-Stokes equation or the Stokes equation, and a hyperbolic equation, which are the plate or the wave equation. So here it's a bit more complicated, and the results are also quite less good. So for example, for the undamped plate equation, it's not so important the regularity I get, but you see that between the initial condition for the beam equation, the initial displacement and the initial velocity, and what I get after that for the regularity, there is a loss in the regularity. So I don't keep this 3 plus epsilon for eta 1 0 or this 1 plus epsilon for eta 2 0. I'm losing some regularity, and this is due to the fact that now the linear system, which is behind my system, is not generating an analytic semigroup anymore. So what I'm going to show is a resolvent equation which is less good as before. So before I have that the norm of lambda minus a power minus 1 is less than c over lambda, and now it's only lambda power 1/2. And it will not imply that the exponential of TA is analytic, but only of class Gevrey, which means that in the derivative, you have a power gamma in the factorial, which is giving less good result in the system. So in particular, when you study the system y prime plus ay is equal to f, you will not get any more the maximal regularity as before. You have you need more regularity for f. You need that it is morally L2 with value in the domain of A1 of A at the power 1/2, and you need that Y0 is like in the domain of A at the power 3/4. So because of this regularity, the linear system is more complicated to study, and the nonlinear system you will lose some regularity. So just to explain a little bit how you get this kind of result. So again, I'm looking to the resolvent estimate as before. So I rewrite exactly as before the corresponding coupled system between the Stokes and the beam equation. Now there is no more damping. There is no more the A2 eta 2, which was helping to show that the corresponding system was analytic. But I only need to show the resolvent estimate here with a power of lambda, which is only 1/2 and no more 1. So to do this, as before, I will put f and g is equal to 0. I will introduce the Dirichlet to Neumann operator L lambda, but here it's not exactly Dirichlet to Neumann because it's Stokes equation and not a heat equation. And the resolvent equation reduced now to just lambda square eta 2 plus lambda L lambda de eta 1 plus A1 eta 1 is equal to h. So there is no more damping, but you are going to use the Dirichlet to Neumann operator, the L lambda operator, because else if you don't use it, you just have a beam equation, and there is no hope to have something which is Gevrey or analytic. So you really need to use this operator, and this is what will help you, because since there is a damping in the Stokes equation, the viscosity, this damping will also have an effect on the beam equation, and because of this, you have some hope to show this resolvent estimate that I've written below. So to do this, my time is almost over, so I will not explain so much, but the idea is to decompose L lambda in a very careful way by introducing two operators, one which is L lambda times an operator which is more or less bounded, and an operator G lambda which behave like one A1 at the power 1/4. So my resolvent equation reduced to lambda square eta 1 plus k lambda eta 1 plus lambda g lambda eta 1 plus A1 eta 1 is equal to h, which is very complicated. So if I simplify first by replacing the g lambda by A1 power 1/4, it's already a little more easier to study. And I find this a very simple equation, which was studied by Chen and Trajan in 1990, and which shows that for a power of alpha which is less than 1/2, so when you have 1/2 it is analytic, but when you have only alpha, you just get this estimate, which is exactly what I need, because I have alpha is equal to 1/4, and by putting in here, I will get exactly the resolvent equation that I need. Then it gives me the estimate I want, but I have to go back to this equation to the one with the k lambda and then to the g lambda. But this is some work, and we managed to do this part and to get the result for the linear system and then for the nonlinear system. So to go on, I will skip a little part of this. So we managed to do also the wave equation, and of course I don't have time to present it, but for the wave equation, what is very nice is we managed to find again an analytic semigroup. So it's no more Gevrey, it's really analytic. And we want, of course, to go on this kind of study. And what we would like to study, for example, is a case where instead of a damping, you have an extra term, which is an inertia of rotation. And this term does not have any damping in it, but because of it, we expect to have an analytic semi-group again. So it was studied by Céline Grandmont, Mathieu Hilleret, and Julien Lecoeur, and they obtained by different methods some maximal regularity property, and we would like to get something similar by using the same approach as we did here. Also, something which is missing in my model is horizontal displacement. There is only vertical displacement. So what happens when there is horizontal displacement? What happens also if we want to do the 3D case or other geometries? And I would like just to finish my talk by pointing out that we also started to do to study the controllability associated to the system, and we do it in a very simplified case. So this is again the Stokes system with a boundary condition, but instead of the damp beam equation, we consider another parabolic equation, but much simpler, which is just the heat equation, and we show that this system is null controllable. So I stop here.
Okay, Takeo, thank you very much for the kind, very nice talk. And does any question?
No questions. No questions.
Well, the audio is open, so the microphone is open. So if anyone has any question or comment, feel free to speak, or maybe write it on the chat. Okay, so Takeo, what in this case is that the controllability issues, it's more delicate, right? I mean, I believe this is the step forward that you guys are hoping to take next, right?
Yes, exactly.
What's the main difficulty, Takeo, in your opinion, to study controllability problems for this kind of equations?
In fact, it was we already started a lot with Rémi Buff in Nancy, and in the case in the equation I presented in the last slide, what was very nice is that you can rewrite the heat equation as a Van Cell condition, which was studied by Rémi. So you can rewrite everything in order to get again a Van Cell condition, and because of this, you are able to get the controllability by only acting on the fluid. But in the case of a beam equation, even a damp beam equation, what is happening is you cannot reduce it anymore to, let's say, a Van Cell equation. You have like another equation. You should add another equation as the equation which is written here, which is the time derivative of another unknown, let's say eta, dt eta is equal to zeta. So you introduce a new unknown, and you have to also control like the position of the elastic displacement. And because of this, we were not able for the moment with Rémi to get a similar result. So it's just some kind of trick that we stop here.
Okay, thank you, Takeo. Anyone else? Any question, comment? Okay, so if we finish this today's talk, okay, so thank you very much, Pierre and Takeo. I really hope that the next time it will be here in Brazil and with you both here. So let's hope to meet in person soon. Okay,
thank you very much.
Thank you very much. And okay, so I'll finish here. I know that's a bit late already in France, so okay. Okay.
Well, thank you, Felipe. Thank you a lot, Professor Takeo Takahashi, for your amazing talk.
Thank you.